Hello everyone, welcome to my talk on how to design a network's topology when its components are moving at speeds of 27,000 kilometers per hour. Let me start by touching upon three fantastic recent advances in space technology. Reusable boosters, which come back to Earth after launching rockets, thus reducing launch costs. Significant reduction in size and weight of satellites, thereby packing more satellites per launch, reducing costs. And automated link tracking, which enables inter-satellite laser communication. Products offering laser intersatellite connectivity at 10 to 20G at distances up to 8,000 kilometers are already available. One caveat is that it takes a few seconds to tens of seconds to establish these laser ISLs. This will later be important when we discuss the various design challenges. The primary goal, it seems, is to build mega constellations consisting of thousands of low-flying satellites, which provide global low-latency internet coverage. SpaceX is leading the front. Their project is named Starlink, and they have already deployed more than 500 satellites in orbit. During the first phase, they plan to deploy 1,600 satellites and start providing internet coverage. Their long-term plan is to deploy tens of thousands of very low-flying satellites. Amazon is working on a similar project named Kuiper and plans to deploy more than 3,000 satellites in three phases, with each phase having slightly differing configurations. Various companies and startups have joined this race and have their projects at different levels of maturity. We here explore how to connect satellites with each other in order to build such networks and deliver traffic effectively. But first, a brief primer on the proposed satellite constellations is necessary to set the context. How do we describe a constellation, and what features distinguish this setting from traditional terrestrial networks? The first descriptive parameter I'll mention is altitude. A geosynchronous or geosatellite has a height of 36,000 kilometers, and the minimum round trip times or RTTs are nearly 240 milliseconds. Low Earth orbit or LEO satellites, on the other hand, fly at heights between 300 and 2000 kilometers, thus reducing RTTs by more than 60x. Another descriptor is orbital inclination. Each orbit here has several satellites. While polar orbits traverse over the poles, orbits can also be inclined. Inclination is the angle between the orbit and the equator. Here, the inclination is 53 degrees. Inclined orbits restrict satellites over densely populated lower latitudes. For polar orbits, the inclination is 90 degrees. Laser or radio links can be used between satellites, with laser offering higher data rates. Typically, there is a north, south, east, west connectivity pattern, which I'll refer to throughout as plusgrid. To the best of our knowledge, all publicly available scientific papers, patents, and visualizations assume the same plusgrid connectivity. A key feature of these constellations' promised connectivity is lower latency over distances beyond a few thousand kilometers. In this example, we are seeing a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being roughly two-thirds in fiber compared to free space means that the fiber path will be 3x higher latency. We'll refer to this inflation over geodesic, in this case 3x for fiber, as stretch. We compared the RTTs between the 8 most populous cities over today's internet to the estimated RTTs over a plusgrid constellation consisting of 1,600 satellites. The estimated RTTs are 70% lower than today's internet at the median. So, if the current RTT is 100 milliseconds, the estimated RTT is 30 milliseconds. The estimates for the satellite network are a bit optimistic though. We did not consider latency inflation due to encoding, error correction, and other factors. But even a 20% increase in this estimate would result in an RTT of 36 milliseconds. We could also see from the plot that the latencies over satellite paths are very close to the geodesic latencies at the speed of light in vacuum. Let us now explore the system dynamics of these constellations. Satellites move very fast relative to the Earth and with respect to each other. If a satellite is now over eastern Brazil, in 6 minutes it will already reach Africa, crossing the entire Atlantic, traveling more than 500 kilometers per minute. Such high highly dynamic behavior translates to links becoming infeasible in minutes. We should keep this in mind while exploring topology design. Having gone through the primer, we come back to the problem at hand. So, how can we connect satellites in order to offer higher aggregate bandwidth, keeping in mind the dynamics of the system? I'll now discuss what are the constraints we consider and assumptions we make. The key constraint of this system is system dynamics. Satellites flying fast relative to the Earth and to each other. But we have other constraints as follows. Setting up links can take a few seconds to tens of seconds, during which time the involved communication units cannot transfer data. Hence, it's important to minimize changes in which links are connected. Also, the maximum number of ISLs per satellite is limited. In our work, we consider 4 ISLs per satellite following all recent FCC filings. I'll also lay out the assumptions we are making in solving the inter-satellite topology design problem. We assume that the satellite trajectories are given. We rely on FCC filings by SpaceX and Amazon that describe their trajectories. While trajectory design in itself is an interesting question, we have not explored it in this work. Knowing what precise traffic will be served on these constellations is difficult. Our evaluation uses traffic matrices drawn from intuition, but the same approach can be used for arbitrary input traffic. Our focus is on the satellite to satellite connectivity. So we assume that the ground satellite connectivity follows a simple range bounded model. We treat plus grid connectivity, which I already touched upon earlier, as our baseline. On that last point, plus grid being the baseline, what are we trying to improve? One drawback of these very local links to adjacent satellites is that one requires a large number of hops to reach distant destinations. On each hop, the end-to-end communication consumes resources, limiting the network's throughput. We'd thus like to build networks that give short paths but also admit high capacity. We don't need to stick to plusgrid's very local links. The key constraint on ISLs is for them to not dip into the mesosphere. This is the atmospheric layer that extends to about 80 kilometers above the Earth's surface, beyond which there is no water vapor present. Given the altitude of the satellites, in this example 550 kilometers, using simple geometry, we can calculate the maximum permissible ISL length, that is about 5,000 kilometers here. This observation opens up a large design space. While at small scale, with few tens of satellites, only simple connectivity was possible, in the large proposed constellations, each satellite can now reach many more satellites. We are still restricted to being able to connect to only a few, though limited by the maximum number of ISLs per satellite. In picking the particular subset of links to connect, what do we optimize for? We use simple traffic matrices which are intuitive for our evaluation. We picked the 1,000 most populous cities and used a population product traffic matrix. Let CT1, CT2, and CT3 be 3 cities with different populations. The traffic between city pairs is proportional to their population product. We also tested a variant which relies on GDP instead of population. Recall that I earlier mentioned stretch and hop count. Stretch is the inflation in latency over the minimum possible, that is traveling the geodesic at the speed of light in vacuum. Hop count accounts for resource consumption and hence congestion. In the paper, we show that lower hop count translates to less congestion. We also define an aggregate metric as a linear combination of stretch and hop count, with alpha being the weight or importance of stretch. Superficially, this seems like a traditional network topology design problem. These are known to be hard even in static settings, but a variety of heuristics are used in practice. One key contribution of this work is showing why traditional techniques don't work here. We tried integer programming, but it suffers from two major shortcomings. It is limited in scalability, runtime is greater than 2 days even for 25 cities on a beefy machine, and the estimate is roughly 10 to the power of 29 days for 1,000 cities. But even if we manage to speed up the ILP by a large factor or use appropriate approximation techniques, there is a more fundamental issue here. The set of ISLs, minutes apart, are more than 90% different. We should remember that ISL setup times are few seconds to tens of seconds. So, even if we could solve the problem optimally for a snapshot, the set of optimal links varies significantly minute to minute. Hence, to maintain optimality, the system would need to break and make a lot of links continually, resulting in significant disruption of connectivity. We also tried random graphs, as they are shown to be useful in other settings like data centers. Although such random graph generation is faster, it also suffers from large number of links becoming infeasible within a few minutes. Regaining lost connectivity is not straightforward, and one would have to break and make many links. Additionally, random graphs are very inflexible and do not allow the operator to decide on the operating point. They simply yield one combination of stretch and hop count without any control over which dimension to optimize for. So where do we go from here? This, this, and this picture have something in common. They illustrate the use of structure and repetition for design, in this case visual design. We apply the same idea of repetitive geometric structure to network topology design. Consider the 1600 satellite constellation. This is the field of view or connectivity for one satellite, which goes beyond plus grid. A motif consists of two links with two other satellites, and this pattern can be repeated throughout to build the network. Note that in this case, two link motifs are sufficient, as remaining two would be filled by other satellites connecting to this satellite. One obvious benefit of using motifs is the fact that they have minimum link churn. We have analyzed three different constellations: a uniform 40 squared constellation consisting of 40 orbits, each orbit having 40 satellites, operating at an inclination of 53 degrees and an altitude of 550 kilometers. SpaceX Starlink Phase 1, which consists of 24 orbits, each orbit having 66 satellites, operating at an inclination of 53 degrees and an altitude of 550 kilometers. And Amazon Kuiper Phase 1, which is again a uniform 34 squared constellation operating at 51.9 degree and 630 km. Most of the results here are for the 40 squared uniform constellation. You can refer to the paper for the other results. Here we plot the average hop count along x-axis and the average stretch along y-axis for the different motifs. Note that both stretch and hop count are weighted by the traffic matrix, in this case the population products for city pairs. Different motifs offer different trade-offs in stretch and hop count, and we can see a Pareto frontier of motifs superior to the rest in both hop count and stretch. Not only do motifs offer performance better than random graphs, they also provide higher flexibility to an operator. Note also that the random graph solution also suffers from link churn. This is where plusgrid operates, with the best available stretch but very high hop count, thus being a low efficiency motif. Note that the slope of this frontier is small enough on the right side such that by sacrificing 2% stretch, one can improve hop count by 32%. This is one of the resulting motifs for the 40 squared constellation that provides much higher efficiency than plusgrid using a combination of long and short links of different orientations. I am showing the two links in the motif in different colors here for clarity. So, the motifs perform well, but can we do even better? Yes, by exploiting the geometry of these constellations. Compare the field of view of a satellite at the equator to one at a higher latitude. We see the constellation is denser at higher latitudes. This translates to more options for connectivity as we go higher up from the equator. This plot quantifies the number of motif possibilities at different latitudes. For polar as well as inclined constellations, the number increases significantly with latitude. For example, for the inclined constellation, there are around 1000 options at the equator versus around 3500 at higher latitudes. So how do we exploit this characteristic? Consider a single orbital plane. A quadrant of the orbit consists of 10 satellites out of the 40 in total in this orbit. We split the quadrant into multiple zones, 3 in this case. Next, we find out the optimal motif for the entire constellation, considering only the motif choices available at zone 1. We assign the corresponding links to zone 1 while removing the rest of the links. We repeat the same process for zone 2 and then for zone 3. This is the final 3-zone multi-motif scheme for the 40 squared constellation we are looking at. As you can see in the plot, the multi-motifs offer higher performance beyond the single motif frontier. Different alpha values result in different multi-motifs, and as we give higher priority to stretch, the schemes move towards plus grid. Putting all of this together, these are the performance improvements above the baseline plus grid connectivity. Starlink sees more than 2x improvement over baseline, while Kuiper also has similar benefits. We also considered settings where links need to be shorter due to power constraints instead of just the visibility constraint we considered thus far. In the most pessimistic case, a constellation must at least allow link lengths that suffice for plus grid connectivity. Even in this worst case scenario, Starlink sees a 40% improvement over plus grid. I'll briefly note that this work is just one of the several satellite networking problems we are exploring. As we discussed briefly, Kuiper, for example, plans to deploy 3 distinct shells which vary in inclination and altitude. We are currently investigating how to effectively connect these different shells for higher performance. Routing is very interesting due to the system dynamics, scale, and latency capacity trade-offs. Also, congestion control poses new challenges stemming from 2 reasons. Number 1, end-to-end path latencies change over time naturally, independent of congestion. And number 2, satellite path changes could result in significant reordering of packets. To help bootstrap research in this area, we are also developing packet level and flow level simulators that capture the necessary system dynamics. Thank you for your attention. I'll be happy to take questions now.